Okay, let's take a peek at some graphs and their correlation coefficients. Yeah. So if we look at this first picture, this data is perfectly lining up. That has a correlation coefficient or R value of 1. So it's 100% linear. Now, in the second graph, you see that, I mean, your imagination can draw in a line pretty well in terms of how this is increasing, but it's not perfect, right? And you might be a little off. Like your graph, if you were to guess what is the best fit line, yours might be a little bit different than somebody else's, and then we would have the computer find the best one by minimizing how much error. So here, but there will always be some error because it's not 100% linear. This one's about 90% linear. It's pretty good. It's pretty strong. And this one, I mean, it definitely looks like you could put in a rough line that's increasing, but it has a lot of error. So it's not that great, you know? I mean, if we were thinking about it in terms of school, like 50%, that's an F. You have to retake the class. By the way, in college, C's get degrees, means that D's do not, right? Like if you get a C, that means you passed. And if you get a D, that means you didn't pass. But anyway, and then these dots, oh, okay, so this is a similar plot to this one, except it's going down, and it's really weak. We could draw a line in here, but there would be a lot of residual error. So it has a lower R value in terms of a percentage. I think interpreting these in terms of percentages make it easier for my brain to understand. And then this one is going down, so it's decreasing, the data is, and it's pretty linear. It's good. It's good, not great, right? It's like, it's pretty healthy, but it's not perfection. And then over here, we see a decreasing linear data that is perfectly linear. Strong, super strong, as strong as you can get in terms of linearity. Okay, so match the graphs to the correlation coefficients. Okay, so we're given 3 graphs and we're given 3 correlation coefficients. Which goes with which? Okay. Well, I'm going to start with the strongest one. So this one is clearly the strongest linear relationship. Uh-oh. Sorry about that interruption. This is clearly the strongest linear relationship, and it's going down. So I look at this and I'm like 99.2, that's this one. And then I look at this one and I'm like, whoa, those are scattered everywhere, not very linear. I can't even tell if it's going down or going up, or it's chaos. So I look for the weakest one there. If I turn that into a percentage, it's 4.9% weak. So the strength of the linear relationship is incredibly weak over here. Okay, so I'm thinking, by the way. And then this one is decreasing, but it's just not great. It's good, not great, right? So that one is our 70%. Okay, so this R value really is just judging the strength of how linear it really is, or measuring it. Let's take a look at this last example from this section. Sulfur dioxide and tombstones. Okay, now I need to make a quick little shout out, because although we use Mercer and Zabecki, and I do like that book, this data set, it comes from this other textbook that I like. Elementary and Intermediate Algebra, Functions and Authentic Applications by Jay Lehman. And just because, I mean, he has some really fabulous data sets. Like, I found this one very interesting, so I plucked it right out of there. Research compared the mean sulfur dioxide concentration, air pollution, and the mean deterioration rates of marble tombstones in 21 United States cities for the period over a century, 1893 to 1993. Okay, so the average air pollution and the average deterioration rate of the marble, right? Those things have been around for a long time, so we're able to actually measure them. The data is in this table. Okay, so you see the average concentration of air pollution in that city, and you see the average rate that the marble is deteriorating in that city, okay, over the century. So how much has gone for that century? And I want to mention right off the bat that when we're entering this data into list 1 and list 2, so we have to make some decisions. We have to decide what we think. So first, do we think there's an association when one variable is related to the other one somehow? So our first guess is that the deterioration of marble is somehow associated with air pollution. Okay, once we're like, yeah, maybe. So we make an association between these two. And then we think, okay, well, how strong is the linear relationship between these two variables? But once we make that kind of association, we think, okay, which one do we think is responding to the other? And which one do we think is explaining the other? So I'm thinking that we are guessing or theorizing that the deterioration rate, the deterioration of the marble, is responding to air pollution. So I'm going to put this as the response, and notice that this is just a really big data set. So the response variable is the deterioration, and I'm thinking that the air pollution is independent from the deterioration. So we're calling this the explanatory. It's the one explaining that response. Okay, and again, these are kind of guesses. We would need more science. So our first is to just make a theory, collect data, and see if there's a correlation or a strong linear relationship between the two variables. Okay, now I need you to know that each one of these represents a city. So before I go to answer the questions on the next page, right, this coordinated pair represents the air pollution in one city and the deterioration of marble in that city. And we notice that if there's a high number here, okay, I've got 1.53 over the centuries, and if there's a low number here, it looks like this number is lower. Now the question is, does that happen in all of these cities, or is it just these two where that's happening, right? But when you're entering your data, you need to make sure that this 180 of sulfur dioxide concentration of micrograms per cubic meter is, oh, they left me a voicemail, is associated with this deterioration of 1.53 millimeters over the century. Okay, so they have to line up in your data values in list 1. And so the explanatory variable I'm going to put in list 1, and the response variable I'm going to put in list 2. But I'm going to make sure they line up because they're coordinated together. They're a pair. They can't go like this, because this would represent a different city, right? These represent the measurements from the same city. Okay. Step 1, construct a scatter plot for this data. Now, I need you to know, I did a few things before this video. I went to Stat, I went to Edit, and I input all of those data values. If you haven't done so, you need to do so now. Like, pause this video and go ahead and enter all of that data. Because now I'm going to go to, I'm going to make my scatter plot. So second, stat plot. I'm going to hit enter on number 1. I'm going to make sure it's on and scatter plot. So I arrowed down to go to that. And I'm going to hit enter. It's on that. My explanatory I put into list 1. My response I put into list 2. So I'm good to go. But now I need to hit zoom. And I need to arrow down to 9 for the zoom statistics. Zooming for statistics. And there is our scatter plot. Okay, so now we need to make a rough sketch of that. Construct a scatter plot. Remember your labels. I will remember my labels. Okay. We are thinking that the explanatory variable is the average sulfur dioxide concentration. So mean sulfur dioxide concentration. And they give the measurement. It's nice to put it in here, but instead of putting that in here, I'm going to say air pollution, just because I feel like readers relate to that more. Now, that being said, it's measured in micrograms per cubic meter. And the response variable we are guessing to be the average deterioration. So mean deterioration rate in a century. I'm just going to put mean deterioration rate. And that was millimeters over the century. Okay, let's draw this. I see a cluster down here. Boom, boom, boom. And I see, looks like 2 of them actually, like very close to each other. Then I see a little bundle of 3 and 1 up here. Okay, as you can see, I'm just making a rough guess for each one of these and their data location. Got it, got it. Don't leave anyone out. And you know it's a really rough sketch when I don't even put any markings on my scale. 1, 2, 3, and then 1 down here, and then 1 up here. Okay, there's a rough sketch of my scatter plot and with the labels. How close is this data to looking like a line? I mean, I'm okay with it. I feel comfortable. I mean, it's not perfect, but I feel comfortable putting in a line here. My imagination can put it in, but it's not perfect. So good. Not perfect, and increasing. So as air pollution goes up, then the deterioration goes up. Find an equation of a linear model to describe this data using your calculator so that it finds the best fit instead of you guessing the best fit, right? So here we go, back to the calculator. And I'm going to go stat, calculate. For linear regression, hit enter. List 1, yes, is where we put the air pollution. List 2 is where we put the marble deterioration rate. And I'm going to calculate. And voila, now I'm going to pull this over here and copy it. Yeah. So find the equation using your calculator. I don't know, you want to round to, oh man. It looks like we should round to 4 decimals. So y is approximately The A value is about 0.0086. There's my X. And plus 0.322. Oh, well, if I round that, I can't round, it's a 99 after that. So really this turns into a 30. I had to round it up. And I still am not a big fan of Y's and X's because they are not very clear. So I'm going to actually change them to, okay, the responding is the deterioration. D is approximately, because not perfect, 0.0086, however many. What is that? The air pollution, sulfur dioxide. Yeah, I'm going to go with S for sulfur plus 0.3223. Okay, there's our linear, here's our initial, and here's our constant change. So if I rewrite this, right, the deterioration is approximately 3.223 initially without any air pollution, and plus 0.0086 for however much sulfur dioxide is in the air. Okay, write down the R value showing up. Yes, I will. Let's see, R is approximately 0.9009, or that's approximately 0.901, which is 90.1%. Whoopsie, I said 0.1, but I forgot to write the 1. And there you have it. Good, not perfect. What is the slope of this linear model? Interpret it. Well, the slope was this constant change here. So the slope equals the constant change, and that is 0.0086. Okay, so what is constantly changing as air pollution goes up? Well, okay, so for each increase of the micrograms per cubic meter sulfur dioxide, of micrograms per cubic meter of sulfur dioxide concentration in the air. Okay, the deterioration rate, deterioration rate goes up by 0.0086 millimeters per century. Voila. So there's our constant change. It increases, the deterioration rate goes up by 0.0086 if there's an increase of air pollution. There, period. 6. Estimate the mean deterioration rate of the marble tombstones during that century in a city where the mean sulfur dioxide concentration, so the air pollution, was 150 micrograms per cubic meter. Okay, for that period. So what are they giving us here? Is this the deterioration rate, or is this the sulfur? Mean sulfur. This is the sulfur. So sulfur equals 150. And so we put that in to our model. The deterioration rate is approximately 0.3223 plus 0.0086 times 150. So D, then, okay, here comes my handy calculator. 0.3223 plus 0.0086 times 150. So add it 150 times. Hold on. Okay. 1.6123 about. Okay, so the deterioration rate is, oh man, more than 1.5 millimeters per century. Wow, got it. That's a really big difference between a third of a millimeter per century to over 1.5 millimeters of marble gone. Got it. A city's mean deterioration rate of marble is 2 millimeters. Okay, so now they're actually giving us the D, the deterioration. 2 millimeters per that century. Estimate the city's mean sulfur dioxide for that period. Okay, well, we're given the D value, so we're going to need to put that in right here into our linear equation. So 2 is equal to 0.3223 plus 0.0086 times the amount of sulfur. Got it. Subtract this from both sides, and it's going to be 1.7-ish. I bet 1.6 something. Yep. Okay, so that means this amount is equal to 1.6777. And now I'm going to scale both sides down by 0.0086. Which ironically makes it bigger because we are scaling down by a portion. So we're asking how many portions are in here? A lot of them. So the sulfur is approximately, okay, so do my division, approximately 195.1 micrograms per cubic meter. That's really a lot. That's a lot. 2 millimeters per century is high, and so their air pollution is high. Because the association is strong, a student concludes that air pollution causes tombstone deterioration. Are they right or wrong? And the question, okay, so these are definitely, I mean, there's a good or a pretty strong, not perfect, correlation between the sulfur dioxide, the air pollution, and the deterioration of marble. Because it's strong, the student concludes it causes the deterioration. Now, I'd be very careful about this word causes again. Okay, so if you are going to make this claim, you are going to need more science to prove it, to use this word. Okay, so I would say to that student, I would be like, careful, do you have the science to back that up? Do you have some chemistry to tell me that it's more than just a correlation, that there's some kind of reaction that happens when you put sulfur dioxide with marble, right? And that causes one to go up or down as the other one changes. So this word causes, it needs more science to back up that word. Okay, so be careful with your language. You can say correlated, and I'd be happy. But you say the word causes, and I'm going to be like, oh, are you sure? Okay, so what did we just do? We used our calculator to enter data, plot those coordinates, and find the best fit line. So what was that? Stat, calc, linreg. We also interpret and make inferences about the meanings of slopes, intercepts, and solution. Now, inferences are because we just used this data to infer about another city, right? Like, we didn't make measurements in that other city. We just made an educated guess based on the data we had. And then we use that correlation coefficient to judge the strength of the actual linear model. Okay, so it's pretty good way to go about finding out if two things are related is to go through this process.